The reason I made this video is because now I get too many results on YouTube and I want to search for infinite sum in the search box. Now I'm getting too many videos about this strange Ramanujan's result for summing normal integer numbers from 1 to infinity. So I want to understand why do anybody want to prove this thing which is not true. It's strange for me, because there is a well-known ancient formula what you also learned in school, that summing integers from 1 to n, we have a formula for that, like n times n plus 1 over 2. This was given by Faulhaber's formula, his naming, when any integer on a specific power, he invented or gave this formula to be able to compute depending on the last number we are summing. So these infinite sum videos refers to this specific line where p equals with 1 and we have just integer number summing. And here's the formula: n times n plus 1 over 2, or n squared plus n over 2. So the answer to this question, if we are summing from 1 to infinity, should be that the result is infinity times infinity plus 1 over 2, which is infinity squared, which is infinity. Why in the earth we want to prove this minus 1 over 12 then, if we know that the result should be infinity? And there's too many videos which wants to explain to us why. And I want to understand what Ramanujan wanted to do, or I made also a little demonstration software with Wolfram Mathematica to see what might happening, or what might happen in some cases, and what should be the real reason why Ramanujan made this. I made a little research and I found out that Ramanujan made a technique for summing infinite series, or he found a formula for an infinite sums. So I found a connection to the Riemann zeta function's particular values here, which also mentions that the zeta minus 1 is this surprising result of minus 1 over 12, which also is strange because the Riemann zeta function is the sum of 1 over n to the s power, and if we are plugging minus 1 in to s, then we should get again the integer number sum. It should be again infinity. But as I see now, that it might be that Ramanujan's formula is related to the Riemann zeta function, and the Riemann zeta function, or every sum to infinity, is the best formula what I have seen until now to compute or approximate is the Riemann, or is the Euler-Maclaurin summation formula. So in my test software, I would like to use this Euler-Maclaurin summation formula to make some tests about the sum of integer numbers or inverse integer numbers, which is the Riemann zeta function. I also noticed here the Ramanujan summation link, which tries to explain, or here is a documentation that Ramanujan wanted or made a technique which, as you can see, is maybe confusing or unclear to some readers. It needs many clarification. It's related to divergent infinite series and is also using the Euler-Maclaurin summation formula in one point, and he just tried to modify it for his needs, because I'm seeing here some infinity. I think this is the remainder term which he wanted to reduce. Smoothed sums, and at the end he is getting this strange or surprising result for the remainder term, or like the remainder term of the Euler-Maclaurin summation formula. It's an interesting integral from 0 to infinity, this complex number including, I don't know. But anyway, when he used his formula for computing the simplest infinity sum like this one, then he got minus 1 over 12 by his formula. So the answer was that Ramanujan invented a formula may be useful for some situation summing infinite series, or for infinite series summing. He invented a formula which might be useful or more useful than the Euler-Maclaurin summation formula, but for others sums are not so useful. And just for fun he posted these values that his formula given this value, strange value. But it doesn't mean that you need to prove that, because it's not okay, it's a false value. So why do we need to prove that when it's not true? We know for sure that it's not true, then why do we want to prove that? Okay, so I want to show a quick demonstration or a quick usage of Euler-Maclaurin summation formula. I put it all together, what you see here, that there is an integral and there is a sum from not even from 1 to infinity, but from a specific start point n plus 1 to an n finish point. And he's saying that the difference by the sum and the integral is this other sum, is the right side sum, which is from 1 to any arbitrary number p, and at the end we will get a remainder, which means that this sum wants to approximate the sum minus the integral, but not all the time approximates very well. So this remainder term might be infinity or a very big number, not just 0. This is like on the Taylor's formula, where we have also a remainder term, and not all the time that remainder approaches to 0 or tends to 0. Sometimes is infinity. And in that case you cannot use or apply the Taylor series approximation. Also in here you cannot apply this approximation if the remainder term is not approaches to 0. And these b, k's are the Bernoulli numbers, which is also inside the Faulhaber formula, because this n squared over 2 is the first Bernoulli number or something like that, and so on. These are, or anyway, in the general formula we have the Bernoulli numbers, like you can see here. So I put all together these 3 lines with a little modification, because I found a mistake in this sum, that this sum should be until n minus 1, not for n. It's better for n minus 1 if you want to use the right side also in the differences of this higher order derivatives. If you want to use n, then in the left side sum it should be n minus 1. So you can see I try to simplify what we saw on the web page. Here's the integral, here's the sum. Now I'm using from m to n minus 1, which by notation of the sum, there is the Greek symbol here, and you are declaring a variable of k, which is from m to n minus 1, and you plug in the f of k here. So the first item is f of m, then f of m plus 1, and until f of n minus 1. This is the shortest notation, but the same thing. And because we are talking about the Riemann zeta function, which is from 1 to infinity, then with a little modification, I made a difference because we want from 1, not from m. So I modified this sum to be from 1 to n minus 1, but then we have to subtract the left side from 1 to m minus 1 to get the exact same result. Which means that this sum is the same with this difference. Just for have sums from 1 to infinity or to something, because of the Riemann zeta function. So altogether, the left side sum minus the integral is another sum plus a remainder term, which at the end, finally we have this expanded result, which is the real Euler-Maclaurin summation formula. Okay, and if you want to apply this formula for the Riemann zeta function, what exactly the Riemann zeta function is that we are summing a function which is 1 over k to the s, so the function itself is this one, and we need the higher order derivatives because of the flat side, which needs a little explanation. For that I also made a little test program. Here we have the function 1 over x to the s, and we are starting to compute the higher order derivatives. Anyway, just for start point I put 0 because the 0th order derivative, the function is itself, which means that x to the minus s, which is the same thing. 1 over x to the s is x to the minus s. Then we compute the first order derivative, and you can see for higher orders what I made here, it's an internal function involved from Mathematica. So instead of, if I'm computing the 8th order derivative, we have this product here. So if you want the 8th order derivative, you have to multiply s by s plus 1 times s plus 2 until s plus 8 minus 1, and multiply by x to the minus 8 minus 1. So just instead of using this product, we can make a compact way, this factorial power, I mean. This is doing the same thing. So the name as factorial power with these two arguments is giving the same thing. So that's why in this nth order derivative I made the notation to fp factorial power of minus s and m over x to the s plus m, because x to the minus m minus s is 1 over x to the m plus s. And one more exception in the integral. The integral should be this one. In general case if s is not equals with 1, but if s is equals with 1, we have 1 over x as the function, and the integral of 1 over x is natural logarithm of x. So there is an exception when s is equals with 1. So why this means, anyway, we want k minus 1 order derivative, so we plug here instead of mk minus 1. We will have this general formula for the high order derivatives and this one for the integral. So the Euler-Maclaurin summation for the Riemann zeta function is this one. By the above formula, and again I made a little order here, reorganized it, that I left in the left side the infinity for the s equals with 1 case, because when s is 1 we are summing 1 over k to infinity, which is the harmonic series, which is the well-known sum of the Euler gamma constant. If you're subtracting logarithm of n from sum of 1 over n or 1 over k until summing to n, when n approaches to infinity, then we have the well-known Euler gamma or Euler-Maclaurin constant. And I move to the right side, so this is how it should look like, the formula at the end, plus a remainder term. So exactly this thing I introduced here in this test sheet of 4 from Mathematica. All these writings are internal for Mathematica, and here are the results for you to understand better what we are testing. First of all, I test for s equals with 2, because this means that the well-known Basel problem, which Euler resolved and had another surprising result of pi squared over 6, and pi squared over 6 is approximately this value. Anyway, we can compute it if you want. So this is the real value of pi squared over 6. And what you can see here exactly is a sum. From 1 to, I made here infinity. I cannot put infinity here, but I'm starting to increase this variable until a very big number. First of all, I made 101 here to be, this is a big number, not infinity, but it's a big number, and anyway can be seen that the Euler-Maclaurin summation formula is approximating this real sum from 1 to 100, which is this value. The approximation of the formula is very good. You can see how much decimal places is approximating. 49 instead of 48.9. So much decimal places is the approximation. Of course, if I put here 1001, then you can see that summing the numbers from 1 to 1000, we have a much more precise value for pi squared over 6. Now it's 1.64. Before it was 1.63. So if this infinity number gets bigger, then we will have a much better approximation. Now you can see that it's 1, 44, 9 and 2 instead of 3. So I will put it back to 101. So this is demonstration for the Euler-Maclaurin approximation formula. Is very good for for approximating infinite sums. What's next? If I'm trying for s equals with 3, then we get the Apéry constant or something like that. Is a well-known constant again. And if you want, I can these constants are usually the zeta. We have a internal function named zeta, and we can use it for s. And Wolfram Mathematica knows these values. So as you can see, n of the number of the zeta of s is nearly the same. So this is a very good demonstration that the Euler-Maclaurin summation formula, how good is for approximating infinite sums. You can put it here. This big number is near the same, it will be. And the approximation, this is the real sum, not for infinity, but for a big number, and the Euler-Maclaurin is not approximating this sum better than the infinity. Okay, now the real reason, we can also test it for 1, because it's the harmonic series. You can see that the sum 1 over 1, 1 over 2, plus 1 over 3, plus 1 over 100 should be a big number. For infinity, it should be infinity. But if we are subtracting natural logarithm of n plus 1 from this sum, then we will get the Euler gamma constant. As you can see, the zeta of 1 is complex infinity, because we are summing this sum without subtracting the logarithm. So in this case, we need the Euler gamma constant to be seen. So this is the Euler gamma constant, which is the same. It should be the same at the end if you are using infinity here. So again, this Euler-Maclaurin approximation formula is very good approximation for everything. And now it comes the best part. What Ramanujan said. What if we are using the zeta function for -1? So the question is, it will give us -1 over 12 or not? Not. The original sum 1 plus 2 plus 3 plus until 100 should be, as the Fairhaber formula said, n times n plus 1 over 2, n 100 times 101 over 2 is 5050. And what the approximation gives us? The same value. So this is the truth. And we had also an approximation formula. It's not even the Fairhaber formula. We had an approximation formula by Euler-Maclaurin. And this formula gives the same value as the wanted one, as the true one from real life. And what gives the zeta of -1? This is -1 over 12. Minus 0.0833. This is Ramanujan's result. I'm removing the Euler gamma. So this is the Ramanujan's value, and this is the real life value. Then, where is the mistake? Or where is the difference? What did Ramanujan made wrong? Let me ask. Take a look back when we tested on the Basel problem. We have this pi squared over 6, for example. If you can see the formula, normally we should use here infinity instead of this variable. If s is 2, k is starting from 1 and so on. So s is 2 plus k, which is 1, the first term. That means it's infinity to the 3 minus 1. So we have here 1 over infinity squared. What does this mean? We have to divide 1 with infinity, which normally approaches to 0. So normally we don't need this term here. We can use 0 instead of it. It shouldn't be much more difference. Let's see what will happen now. As you can see, the approximation formula again approximates the real value of the infinite sum. It's true that some decimal places are wrong now. It's slightly worse than it was, but the same thing it approximates. So we don't need this term in this formula, and also it will be good. So that's what I think Ramanujan's made, that he observed that this term is all the way, if even from s equals with 1, we can have the same thing. It's again approximates the same thing, so it's no need for this term here. We can zero out the inf variable here. So for all the values where s is greater than 0, 1, 2, 3, we get the same thing here. It's also useful for approximation. And now if we are plugging back -1 to test the real integer number sums, then it will be the surprise. And we forgot to put back this value, just using 0. Then we will get the surprising result. And this result surprised me too. But the good thing that now you can see at real time how mathematicians making mistakes. Why didn't you said that I forgot to put also here the 0, because this term is also 1 over infinity, as s is bigger than 0. So again, put it back to the Basel problem and put also here a 0, and let's see. Oh, it's even better, the approximation. Instead of, it's very good. Let's see how good is this. Because the original value is 930,668. What the heck? How many decimal places are correct here? 4822. 48 instead of 4825, it's 4822. So much more decimal places we have now for the infinity sum. Okay, but now this is what matters. Let's try again for the harmonic series. The logarithm of, again, the Euler gamma. Okay, 7721 again. It's approximates better the infinity sum than the original sum until 101. Okay, so try again. Put now s instead of the positive ones, put a negative value like -1, which what will compute for us? Now you can see the real reason why the Ramanujan's formula or summation technique is giving us the surprising result of summing normal integer numbers until infinity as minus 1 over 12. This is the same result as what the zeta function is using in Wolfram Mathematica and in these other posts and Wikipedia sheets where it was the Riemann zeta function for particular values. It's minus 1 over 12. Let's see what will happen if I put minus 3, because it should compute 1 over 120. If I put here minus 3, it should be the same result with 1 over 112. Yes, it's the same value. Try another one to be more sure. Minus 5. I put here minus 5. What it should be the value? 252. So voila, minus 0039, minus 0039, minus 0039. The same thing. So the conclusion is a big mistake here. Instead of using an original golden formula like the Euler-Maclaurin summation formula, if you forgot to use the original term here, then we get the exact same wrong value as Ramanujan's summation technique gave us. But it shouldn't be like that. If you can put back the normal formula, normal term here, then it should compute the exact same value. Or something like that. What's wrong here? 1, 1, 1. What is this? K, what K? Ah, sorry. It's not K, it's minus 1. Yes, because okay. Yes, voila. Here's the exactly same approximation value if you are using the original formula. Just if you forgot to use it and you are substituting with 0 because you think that s is greater than 1, then 1 over infinity should be 0. And just in that case, we have the same wrong value as Ramanujan's summation gave us. So that's the explanation. This is a very simple explanation that just a minor mistake will ruining everything if you are not working correctly or not observing this. If you are making mistakes, you will end up in wrong results. So that's it. Thanks.